All right, just some quick rules for using Newton's law of gravitation. Fg equals gmm over r squared. What you can do with the equation, and also importantly, what you can't do with it. So first off, the easiest thing to use the objects for, or the equation for, is point masses. So objects where all of the mass exists at a single point, or where they are far enough away from the other objects where if you just sort of squint, you can pretend that they're at a single point, and it'll be good enough. And so if M1 and M2 are point masses, use the equation exactly as you expect, and r is just the distance between them. Now, that works fine as long as the objects are small enough that you can consider them point masses and compact and really far away from each other, so we don't really have to care about their shape. But there is one shape that even if the objects are close to each other, you can still treat as a point mass, as long as they are not overlapping. And so if one of the objects, that shape, is a spherical shell. So if one of the objects, or I guess both of the objects would be fine as well, but if one of the objects is a uniform spherical shell, uniform meaning it has constant density, so there's not like a heavy half and a light half. Spherical meaning, it's a sphere, it's ball shaped, and then a shell meaning that it's hollow, all of its mass is on the outside. So if one of the objects is a uniform spherical shell and the other object is outside that shell, okay, so if one of the objects is a spherical shell and the other object is anywhere in space other than inside the shell, then the shell can be treated as a point mass with all of its mass at the center of the spherical shell, at the center of the sphere. And this is why, when I originally introduced the equation, I said that r is just the distance between the centers, because for most of the objects we work with, they're just big spheres. They're planets and stars and things that are basically spherical. And so if you're dealing with a bunch of spheres, you can just pretend that they're points located at the center of that sphere. And so you just measure between the centers of the spheres, and that gives you your r. Some of you might be thinking, well, wait a minute, this says a spherical shell, and a planet is not actually a spherical shell. It is a solid sphere. That's actually okay. That is our next rule. Is going to explain why that's okay. So if you have a more complicated shape, so something that is not a point mass or a uniform spherical shell. So if you got for more complex systems, so this could be if you have multiple objects and you're trying to figure out what the force of gravity is from all of them. Or if you just have a shape that is more complicated than just a spherical shell. And of course, we know we can treat a more complicated shape as just a bunch of objects. If you have more complex systems, so come into focus, multiple objects, more complicated shapes, etc., then we can use what we call the principle of superposition. which says that the force of gravity exerted by your system is just equal to the sum of the forces of gravity of the parts. So if you have an object made up of 2 3 spherical shells, then you can just take the force of gravity of all of them and just add it up. And that'll tell you what the total force of gravity from that entire system is. And of course, if you are dealing with a planet, it is just a whole bunch of spherical shells. You can think of like the rings on a tree, except this is spheres going inwards, so it's sort of like the rings on like a jawbreaker or something, I suppose. So the planet doesn't have to be uniform density throughout. It's just if you divide it into a whole bunch of spherical shells, each one of those shells, as it goes down, has to be uniform, or close enough. And so like the Earth, the very outermost shell, I guess, is a combination of water and rock, and it's not quite uniform, but very, very quickly we get into pretty uniform layers of rock and then uniform layers of magma and the iron core and stuff. And so you can treat pretty much any solid planet, star, whatever that is spherical as just a sum of spherical shells, in which case you can treat all of them as though they are at the center of that giant sphere. And you can just find the force of gravity of all the parts, which is going to be the same as if you just use all of the masses and put them at the center. And so when you're dealing with solid spheres, you can just treat all of the mass as though it's at the center, as long as those spheres are within their shells uniformly symmetrical. And of course, if you have a more complicated shape, then you have to do some other addition. But if they're spherical shells, they all just add up. And of course, if you have an infinite number of pieces you are adding together, whether it's an infinite number of shells or an infinite number of point masses, we can also write this as an integral. So if we just figure out what all the infinitesimally small forces of gravity from each infinitesimally small part is, and you sum up all of those forces of gravity, that will give you the total force of gravity from your system. There's lots of ways we can use this. Certainly it's how we're going to have to deal with shapes that are not spherical shells, but also, like I said, if it is a solid sphere, the nice result of this is that we can just treat for our solid spheres all the masses being at the center. And then the last rule has to do kind of with this first rule. I said, well, the other object has to be outside the shell. Well, what if the other object is inside the shell? And so that rule is that inside a spherical shell, inside a uniform spherical shell, the force of gravity from that shell is just going to be 0, which means that if one of the objects is a spherical shell and the other object is outside the shell, well, then you just treat the shell as a point mass in the center, and if the other object is inside the shell, the force of gravity is 0, because you just, the shell doesn't do anything. And we can sort of imagine or visualize why that is if we imagine sort of like a side view. Keep in mind this is a spherical shell, not a circle, but and you imagine you have a person inside of our shell. So imagine if like the Earth was actually hollow and you went inside of it. What would happen? According to this, there would be no force of gravity because you'd be inside of the spherical shell of the Earth. Well, why is that? Well, let's just sort of divide this up into sections. So we would have these two sections here, which hopefully are pretty obviously symmetrical, and so they're going to pull equally hard in opposite directions. And so they're going to cancel each other out. And then we have these two sections. And so this part of the spherical shell is much smaller than this part. So it has a lot less mass, but it's also closer. And we know when we're dealing with the force of gravity equation that if you have more mass, you're going to get a bigger force of gravity, but also the closer the mass is, the bigger that force of gravity is. And so what winds up happening is these two pieces they wind up having perfectly opposite effects. This is a smaller amount of mass, but it is closer. And it winds up having the exact same amount of force of gravity as this larger chunk of mass that is further away. And so they wind up pulling equally hard in opposite directions on our person, and they also are going to cancel out. And so the end result is that the force of gravity on any object inside the shell is just 0. And so if one of your objects in the force of gravity equation is inside the other one, and the other one is just a spherical shell, well then there's no force of gravity. Now, if the other one is a solid sphere, it's not quite that simple, and we're going to do a problem with that, but certainly if it is a spherical shell, you just don't need to worry about it. There is no force of gravity.